sufficiently advanced technology is indistinguishable from magic.
Welcome, everybody. It is not frequent that I get to talk to not only an eminent cosmologist, but someone who's also a friend and a very deep and critical thinker. And that is Dr. Anna Ijjas, who is joining us all the way across the country, I believe. Anna, where are you joining us from today?
Right now from the New York area.
New York, where I got my personal Big Bang began 50 years ago in New York State. And it's a delight to talk to you. Thank you for agreeing to come on the podcast.
Thanks for having me.
You know, I'm teaching cosmology this quarter, and it's an undergraduate course. And we always conclude with the most interesting thing, which is where did the universe come from? And and the honest answer is we don't really know. But I want to ask you, what is the most fascinating aspect of, why did you become a professional cosmologist? There's millions of things you could do. Why did you become a theoretical cosmologist?
No, that's a great question, because I didn't exactly have a straight path. You know, I didn't go to undergrad and afterwards decided I will do a PhD in physics and that will be cosmology. It really is that I did first a PhD, a quick one, and I was writing about the philosophy of science. And then afterwards, you know, I was done. I was 25, and people told me, well, you are so young and you have a physics degree, so why don't you look if you want to do another PhD? In Germany, it's quite common that one does 2 PhDs. And why don't you look if you want to do it in physics? You had such good grades, you know, talk to some people. And, you know, I was talking to the person who was the second reader of my thesis back then in Munich. And he said, well, why don't you look into cosmology? Because if some big discovery will be happening soon, that probably will come from cosmology. And, you know, I really cannot explain why I took that, you know, at face value, but I just then started to take cosmology courses. I enrolled as a PhD student, and it was fascinating. I was really lucky. I got my first cosmology course I got to hear it with Slava Mukhanov. He's one of, you know, the best person you can learn from. And I just think I really liked it. And it really, a lot of questions really intrigued me. And I really liked also the question that, you know, as a cosmologist, and I'm sure this is something that you enjoy too, you really have to know a little about every part of physics. So I think the combination of first, by somewhat of an accident coming to the subject, but also, you know, the fact that I would say I'm a conceptual thinker. I like, you know, on the one hand, I like to go into the smallest details of the equation and the computer program. On the other hand, I also like to keep the big picture. And cosmology is such a perfect subject for people who like both parts of the story, both the details and the big picture. And but you know, really the most fascinating part of this is that we have so many open questions in cosmology.
Yeah.
And then perhaps, because we are talking, you're an experimentalist, I should also say, you know, what's more fascinating that we have experimental access to all these questions. So coming from the philosophy background, you would think, all those questions, where does the universe come from? Where are we going? What is our place in the universe? Those are all more metaphysical questions. And then you realize, no, actually, you guys can go out and measure all the theory and test all the theories that we make up. So that certainly adds to it, why it's so fascinating.
Yeah, I agree with exactly your perspective. In fact, when I teach my students, the first day of class, I say, this is the only subject in the entire physics department that covers every subject in the physics department, except for one, which is biophysics. I have yet to get into how biophysics works into cosmology, although I do talk about the origin of life and things like that. Maybe it could be someday I'll get some, you know, I'll do a lab demonstration. I started doing lab demonstrations. You know, these classes are so theoretical. I use this book by my friend Barbara Ryden, which is a wonderful book. And, you know, everybody in it and everything in it is, you know, incredibly theoretical, except for, you know, we get into derivations and so forth with the Einstein equations and GR, and you and I will talk a little bit about that. So I just said, I wonder if anyone's ever did, you know, experiments, you know, demonstrations in cosmology. It turns out there's a lot of things you can do. We have black body radiation, we have acoustic oscillations, Tomorrow I'm going to be doing some nuclear physics demonstrations. I'm going to be splitting the atom and no, I'm not going to do that. They won't let me do that without some waivers, but they will. Hopefully I'll get some heavy water, some D2O, and I'll bring in some deuterium into the class and show them how regular water ice cubes float, but deuterium ice cubes sink in ordinary water. We'll see if that actually works out, if I have the budget for it. But it's fun to do experiments and people love it. And yet a lot of what, most people are interested in when you talk to people like your colleague, Brian Greene, or I've had on Neil deGrasse Tyson, and I've had on Michio Kaku, and all sorts of great names. People are really interested in things like, well, can can a wormhole, tell us about ADS-CFT and black hole information paradox? And some of these things are highly philosophical, and yet we never teach our students about philosophy. So I think you came at it from a great perspective, starting with the philosophy, moving in theoretical domain. And I wonder, from your perspective, since you brought it up, I tell my students that it's harder to be an experimental cosmologist because not only do you have to know everything in your field of experiment, but you have to understand the theory of what's behind it. But I say you don't have to do new theory. In other words, I don't expect them to do the brilliant things that you and your colleagues and your students work on, but I do expect them to be familiar with what you're doing, but not create it. What do you feel for an educated person as a theorist? What is the experimental minimum, to use Lenny Susskind's kind of terminology? What would you say for a theoretical cosmologist? What should he or she know at a minimum about experiments in general?
Well, as much as one can. I think that there is, difficult to say the minimum. I never thought about this. I think, maybe if we go concrete, I think a theoretical cosmologist should definitely be able to read a paper that is about, let's say, CMB or dark energy or any survey data. And not just to read it, but also understand the statistical methods, can read the data, the maps. So I do think that, it's important not just to, let me say it this way, it's not enough to know the 6 parameters. I go to the paper and look at the 6 cosmological parameters and I find what I have to fit with my theory. That's not the minimum. That's not even step -1, I would say. I think, it's really important to be able to, converse with theorists and know of the ongoing experiments. I think it's really, experimentalist, I said theorist. And know what the most important experiments are. I also think it's very important, at least for me, it's very important. You mentioned, we actually know each other to talk to experimentalists. So since it's important for experimentalists to talk to theorists, I think it's really important to know your experimentalists. There are different experimentalists, go about the experiments differently. They have different interests. They have, different, just as theorists have different strengths and weaknesses. I think it's really important for theorists to personally, so beyond being able to read the paper, I think the minimum is also that you know at least a bunch of leading experimentalists personally. So I would add that definitely, know your experimentalists, know whom you can ask about something if you are not quite sure, follow every release, be up to date and don't say, oh, I'm a theorist, I don't have to know everything. Know what a jackknife test is if you wish. Know when you guys go to Atacama, what everything it takes and have respect for what experimentalists are doing. I mean, I have an immense respect for you guys, what you are doing. It's just really amazing. Just the fact that, I suffer from altitude sickness, just the fact that you climb up those mountains and spend a lot of time to build those telescopes, just this minor aspect that's for you probably second nature. I think it's really important that apart from, the theoretical minimum of experiments, you have personal relationship and personal appreciation and understand that it's really important to talk to one another. Learn the language what experimentalists will understand, and experimentalists should understand what theorists. So I think it's just like, be friends, be good friends. That I think is the minimum. Yeah.
And have an open mind, open attitude that, it's that it takes both of us to do what we do. And I think, what's interesting to me is that, we come to the conclusion, the kids take this class, presumably because they're interested in the beginning of the universe. And on the first day, they're disappointed because I say, we don't really discuss the beginning of the universe because, first of all, we don't know if there was a beginning, a single beginning. B, we don't know much about its visibility and viability, but also because the subject that we study just like biology, you don't start with the origin of life when you take a biology class. You start dissecting frogs, or I don't know what they do in biology. But I think the dean needs to check them out. But in reality, we don't really start with cosmogeny. So most people, I don't teach cyclic cosmology in my cosmology class, as interested as I am in it. So to what extent do people object to the study of the cyclic universe? What is the kind of objection that people most present about the cyclic universe idea?
I think we have to start probably historically what used to be the objections, and very often people come back with those objections also just to know if one already has an answer for them. So as you mentioned, probably if one took a survey among all people in the world, we would find more people who, for one reason or the other, whether it's religious, whether it's due to their upbringing, we would find more who have some cyclic worldview. So that's I think comes very natural to people in certain parts of the world, and people who grew up perhaps in a more Western culture think more linearly, think that there has to be to everything a beginning and an end, and in between some trajectory, very causal, linearly directed thinking. And so there, everything comes from, I think you feel a little uncomfortable. So I think the first feeling is, this is not what I learned. When I was a child, that I went to school, I always heard the universe had to have a beginning. That was some sort of an explosion, and that explosion gave rise to everything. And now you come to me and say that the Big Bang, even if it happened, wasn't an explosion, but maybe it didn't happen. Maybe it was just a transition from a contracting prephase. And I think that one really has to take it seriously. And this is always the case, right? When we teach people something in physics that's against our everyday intuition. It doesn't really matter whether it's energy conversion or whether it's, gravity or quantum field theory. It's always the fact that people are uncomfortable with the idea that that they grew up with might not be the idea or might not be how nature works. So I think that, that is the basic attitude right now in certain parts of the world, and most physicists grow up with this idea. So I think that is really something that I take very seriously, that, people come with some preconceptions and they like those preconceptions. And then comes the physics, right? So when we, the first time realized that Einstein's theory of general relativity describes the evolution of the universe on large scales, then Alexander Friedman also realized that the universe could choose three different ways to evolve. And so it could expand, it could contract, or it could oscillate between, and he called it an oscillating model, between contraction to expansion, contraction to expansion. And that was, he called it oscillating universe, but this is, I would say, the first modern version of a cyclic universe. Now, there were some issues with Friedman's model, and that was very quickly pointed out by Thorman. So Thorman was the person that is being most often quoted when it comes to what's wrong with the cyclic. Why might the cyclic universe be a wrong idea? And we will probably get back to this, but Thorman is very often quoted in a way, already Thorman has shown that somehow a cyclic universe violates the second law of thermodynamics. So I think that's what some people call it, the entropy problem. So this is the thing, the critique that most people would bring up, not necessarily because they believe in it or they read Thorman, but you have heard it one way or the other that probably a cyclic universe has some sort of entropy problem. So that's
because you're collapsing, because in his model.
Yeah, so there are three aspects of this problem, and you tell me as to what degree you want to dive into this. But Thorman had this aspect has three problems, or the problem has three aspects. Sorry. The one is I turned around the sentence. The first one is that as Friedman imagined it, and that was the model that Thorman criticized. Every single cycle is the same. So the universe contracts, then bounces, then expands. Contracts, then bounces, then expands. And the contraction happens in a way that all physical distances eventually, and we know it doesn't make much sense since we since then know that is just from the quantum perspective not make sense, collapse to a single point. Right? That is, and that everything crunches into a point or a point-like something. So all black holes in the universe collapse together, and there is some big mass created. So that was one of the aspects of the problem. There are two more aspects of the problem. The second one is really the question: if everything crunches, do you need to infinite entropy state? How can you get out of that phase? And there was a third aspect to the problem, and this is a more modern aspect to the problem. That was people were, and I have thought a lot about that aspect, namely how does space-time. So people believe for a very long time, up until I would say a few years ago, that contracting universes, so Einstein behave in a very specific way. And now we have to dive in a little bit, and because if you ask me what would be the most serious problem, it will turn out that the problem that people talk least about is physically the most serious problem that you have to overcome. And this has something to do with the fact, again, we go back to where does our intuition come from contraction, and how does Einstein relativity tells us all of our intuition, actually, how we imagine it is wrong, it's Newtonian. And it is really the idea, if I tell you, you have to imagine some contracting space or space-time. What you will think of is inhomogeneity is growing, everything is collapsing eventually. Probably a mass is being created, or you end up with a big black hole, right? That's what most of us first think of. A contraction, gravitational collapse is contraction. So a contracting universe is perhaps like a big black hole, is a black hole in the making. And that's not exactly a good condition for transitioning to a universe that is simple, flat, smooth, as beautiful as you can imagine, from the distribution of the geometry and then from a matter perspective. And I promise, our intuition is never really right within Einstein gravity. Now, it turns out, really, if you look at contracting universes, contraction is anything but collapse. So instead of the gradients growing, Einstein theory tells you, and it has been a long time conjecture, and mathematicians have been lately proving theorems about it, and I have been doing simulations, full numerical relativity simulations, just the same methods as people use to simulate colliding black holes, to check this conjecture, which says contraction is not collapse. Instead of your gradient, your inhomogeneity is your mass growing. Space-time, as it contracts, it actually inhomogeneities vanish, and you become, instead of inhomogeneous, you become anisotropic. So only thing what matters is all gradient, all connectedness within space-time vanishes. So instead of a collapse, what happens is space-time point starts to develop independently of one another. And so contraction is not collapse, but is it good enough? Is a homogeneous but anisotropic universe good enough for a bounce? Well, no. If you might want to show now one of the simulations as I send you, and I can show that to you. So we know how contracting universe, we can check it, and it's really true that the gradients vanish, but what happens is something that's one calls a mixmaster chaos or mess. So because the space-time points develop independently of one another, what really happens is that in each point, if you were sitting in one point, what you would observe is that in one direction space-time contracts, into other direction it expands, and at different rates. And this is not great, because what happens is really that's why people call it chaos. It's a chaotic behavior of the geometry itself. And this is a third aspect of what we can call under the Tolman problem, that a contracting universe one way or the other is not a good precondition for a bounce, for transitioning to an expanding universe. So that's, I think, if you are a really sophisticated reader of the literature, these would be the three critique points that you would quote. What could be the problem with a contracting universe? It's the crunch problem, it's the entropy problem, or contradiction with the second law, and it is the mixmaster chaos problem, that space-time geometries become really crazy. Even though you don't collapse, you become chaotic and very anisotropic. This was a long answer for a short question.
Right. So do you think it's sometimes I feel like a lot of these things are problems of marketing, and because we're so used to teaching the story of the Friedman equations, and it's so rich to teach the relativistic equations, which can involve things like the spatial curvature of the universe. But you and I just finished singing the praises of my experimentalist friends, ranging from, Lyman Page and the Toko experiment back in 1998, and then the Boomerang and Maxima experiments in 99, 2000. We've known for 22 years now that the universe has zero spatial curvature, and yet I spend a week teaching my students out of the 10 weeks I have about this. So is that because, the math is so elegant and so beautiful, even though, we don't teach about, there used to be that the universe could have essentially, begun from from a static or quasi-static state. And actually, we don't know how. Is it a problem of advertising or marketing, or is there some other reason why you think that people aren't as familiar with cyclic universes in the context of the history of cosmology, but even current work and investigations? Do you feel like there's basically a marketing problem, so to speak?
That's a tough question. I actually think you can call it a marketing problem, but I believe that, very often we teach different subjects in physics as people, as ideas developed, how we came to know about them. For example, so when you mention spatial curvature, so a lot, and we should also praise the theorist of the last 40 or 50 years, how we came to our current model, how we just came to appreciate that we might need something to patch the old hot Big Bang model that, really describes our universe. We call it hot Big Bang, but it's really the description between, let's say, nucleosynthesis and today. That people realized, first, they looked out to the universe. Those were, your previous colleagues, starting with Friedman, and said, this is the universe is expanding, and its geometry, you already named the Friedman equations, is very elegant. It doesn't matter where you are, in what direction you look. That's what we call homogeneous and isotropic. It's everywhere the same on large scales. Of course, not on small scales. This is crazy. Well, everything looks different when we look around. But if we go to large enough scales, beyond the scale of galaxies, then everything looks very elegant. And you would think that simplicity is, maybe this is very natural, right? So that's what we're doing. How could it be different? Why would it not be simple? Why would it not be the simplest possibility? And I think, in science, it's really important to be unconventional very often when you want to find something new. And people said, let's check it. And let's check it again. Einstein relativity. What does relativity tell us? What if let's just run the movie backwards, starting from today? Would it be, let's just with the simplest deviation. And the simplest deviation is your curvature term. Let's see if that curvature term remains small if we start with it being small today. And a lot of people discovered it's actually growing, right? So what really happened is that there is an instability. Even if you start with small, but not exceedingly small curvature, you would have to see today, given the equations that you use to describe the large-scale evolution, what you would have to see is large curvature contributions. And that's how, that was really, I think, a very, very short history to the upcoming of this discomfort that maybe the hot Big Bang theory is incomplete. And that's why I think, one teaches it this way. Now, and that was also a very important insight that led then to the development of inflationary cosmology, out of which I should say then the cyclic considerations grew out. So some people who developed inflationary cosmology were also the same people who were the first contributors to the cyclic cosmology. And then I think, it is really just, it stuck this explanation that, we just look at the Friedman equation with some curvature because it has been so helpful in the past. But, what many people don't teach, and I find, looking at just the contracting solution of the Friedman equation so educational because it tells you so much about, you just learn so much about how gravity behaves in the context of Einstein relativity. That we believe is a description of gravity on many, many scales is a correct description. And so if I think that both the relativists and the cosmologists just teach it for the first, the first reason should be you learn so much. First of all, most people don't know that the Friedman equations, right? They admit both a contracting and an expanding solution. And it's in the initial conditions. We tell the equations whether we want to have the contracting or expanding solution. Why don't we not teach it? I think it's historical. And then now you tell me should one teach it? Yeah, absolutely. Absolutely. One should teach it both to get the right intuition about gravity, but then afterwards, you know what, and that's what I got so excited about is, you know, it really opens up a completely new set of possibilities that might be actually the right explanation of what we see when we look out, for example, into the microwave background. So I would agree with you again. Yeah, it has a marketing problem. Yeah.
Yeah, I think so too. And actually, you know, when I think about even the explanation that inflation purports to provide, I think where inflation has been successful is not in explaining where the universe came from or explaining where the elements came from or all sorts of things, because oftentimes it raises more questions than it actually answers, but rather as a theory of structure formation. And before we get to how structures can occur in a cyclic and the new cyclic cosmology that you and others have developed, I wonder if we could, you know, kind of explain this most common objection that I spoke about with Will Kinney a few months back for his book, An Infinity of Worlds, which involves, you know, doesn't shy away from, you know, the kind of quantum runaway, as you guys call it, the multiverse problem. In fact, it embraces it as a core tenet of his work, which I endorsed on the back of his book, along with your friend, the other more popular Brian of Cosmology there in New York City area. But I want to ask you, what he seemed to say was a objection to the bouncing model was this issue of geodesic completion. I wonder what does that mean, and why doesn't it afflict the bouncing model just the same way, or the inflationary model perhaps? Is it maybe worth detouring first to talk about the Bourde-Guth-Vilenkin theorem, and can you talk about what is a geodesic and what does geodesically complete mean, and then maybe we'll get into this BGV ideas.
Maybe, but you know, it's actually a really technical concept, right? So I'm very happy to talk about it because
my audience is the most brilliant in the whole universe or multiverse, according to
That's great to hear. No, I actually just attended a conference last week, and I was chatting with Roger Penrose about geodesic completeness in cyclic cosmologists. So we share a lot of, you know, intuition ideas how it might work. But let's get back to, I mentioned Roger for a particular reason, because one has to start really with him and Stephen Hawking when one starts to talk about geodesic completeness, since geodesic completeness is really a technical feature of Einstein gravity. And this came up in their first, and probably up until today more prominently probably than the BGV or Bourde-Guth-Vilenkin theorems, the Hawking-Penrose singularity theorems. They actually should be called incompleteness theorems, because what they show is that in a certain sense, so if you follow the geodesics is the path that within relativity massive particles travel. And the question was, you know, how far back in time can you follow the path of massive particles? Finitely or infinitely far? And what Penrose and Hawking have shown, very simply speaking, so none of my mathematicians friends would, you know, probably approve this at a higher level, but if you want to have the shortest explanation, and they say what they have shown is that general relativity is incomplete, geodesically incomplete, because within finite time, massive particles reach a singular surface. Your audience is brilliant, so I can call it this way. So they reach a singularity. And that's how the singularity theorem stuck, but it's really a geodesic incompleteness theorem about relativity. And what Penrose and Hawking have been interested in, or very interested in, were expanding space-time that expand at a decelerated rate. Let's say simply matter or radiation-dominated space-time. That those space-time that were also well describing the hot Big Bang model, those space-time that start with maybe radiation domination and then matter domination, would apply also to space-times that are matter-dominated or universes and are described by Einstein gravity. And now that and it's very simple. Now that you have this concept of what they were following the trajectories of massive particles. What Bourde-Guth and Vilenkin added to is they extended the theorem to space-time that involve an inflationary pace, that involve acceleration. And they have shown that space-time that are expanding at an accelerated rate, inflationary space-time, for example, are also geodesically incomplete. So if you follow the path of massive particles, then what you will see is within a finite time, in certain coordinates. They called it conformal coordinates, but this is really technical. So that the important thing was that you reach a singular surface. That was important about Born-Guth-Vilenkin. Now, why is it important? Why would one care about technical terms in cosmology? Well, some people actually use this to show that the universe necessarily needs to have a beginning, right? And I think that's when one goes beyond what the mathematics tells you, what the theory tells you. It's really a feature of a theory. You cannot tell if you just use Einstein gravity, then the equations break down after at a certain point.
It's more like a no-go theorem, which is one of my problems with a lot of inflation. You know, with the slow roll conditions, I often hear, and I can say this because I'm not working in this field, even if you don't, subscribe to what I'm saying, but people say, oh, the slow roll inflation ends when the slow roll conditions end, when they're violated. But I'm like, well, wait, how does the inflaton know anything about what we call the slow roll? It just seems like that's a consistency problem for us to deal with. But it's like if they say about birds, birds don't really need the study of ornithologists to know how they go about their daily business. So isn't this just saying that the math breaks down at a certain point, and what we have now needs a quantum theory of gravity, not that there's a Big Bang or a singularity? Isn't that sort of an interpretation?
I think this is a perfect interpretation of it. By the way, Penrose, who introduced the singularity theorems, works on cyclic cosmologist, right? I mean, I know that Roger is your good friend, so many people, because I should have started, maybe I should not quote Tom, and maybe nowadays, of course, many people say, but don't the singularity theorems prove the Big Bang? No, they prove really, as you said it. I don't think that one can say it better than you said it, Brian, that space-time, no, honestly.
It's a high praise from you.
But if it's true, one has to say it. That the Einstein equations are not, well suited to explain whatever is what you call either the Big Bang or a bounce or whatever, or in Roger's model, a transition from one, as he called it, eon to another. This is exactly what it is. But I don't think that it's good to. In a certain sense, is it important? I also think that it's important because whenever we can point out a limitation of a theory, that opens up a new question. We know, this is really important. The singularity theorems or Born-Guth-Vilenkin are important because we know that those if we want to explain where those space-time come from as theorists, but also then later as experimentalists, you should be interested in explaining and then showing it, then we have to know what the limitations of our theories are. And in that sense, it's helpful. But of course, that's what I'm saying, perfect formulation. It doesn't tell anything about what replaces the Einstein equations there and what physics that replacement.
Mm-hmm.
Know about the theorems. So it's mathematics. So the theorem rests on certain assumptions. And one assumption is, of course, that gravity is described by Einstein relativity. But there is a more important assumption. These theorems rest on the assumption that the masses of particles remain constant. And that's a very strong assumption. And under that assumption, and it was already shown, if you read the, I think, second to last or something like that, the last column in the printed version of Born-Guth-Vilenkin paper, they show that under that assumption, you can have a cyclic universe that includes infinitely many cycles and is nevertheless geodesically incomplete. And this is true. This is definitely where the field was about 20 years ago. So whatever cyclic model I would take, whether this is the model that I work on, whether it's the model that colleagues worked on, let's say whether it's Steinhardt-Turok, whether it's Brandenburger, whoever works on these models, as long as you keep the mass of your particles constant, the theorems apply. And as long as your theory of gravity is Einstein gravity or certain energy condition, as we call it, which is somewhat of an equivalent statement, are satisfied. Now, that was a brilliant recognition. And I think it came from really two directions. One of them is Roger, and the other one were Itzhak Bars, who is actually very close to you, sitting at the University of Southern California, Neil Turok and Paul Steinhardt, in about a little bit over 10 years ago. They say, well, we know from fundamental physics whether you think of the Higgs or whether you think of some sort of symmetry restoration in the early universe, that is probably not true that the masses of particles remain constant. Whether due to the Higgs mechanism that, for example, and that was the Bohr-Steinhardt-Turok idea, the particles gain a very big mass during contraction, or the Penrose is a beautiful pendant idea that maybe due to the restoration of conformal symmetry around the transition from one cycle to the other, the particles become massless. So in two ways, you can break the assumptions of the theorem. And, really, this is unfortunately not my idea. I was a grad student back then. I wrote to you earlier, and I was really envious of this idea because then you can compute. Physicists talk about it, and I'm sure your audience knows it, since you have had a lot of more technical discussions with guests than with me. And that one formulates this question of how far can I track back the world line of massive particles in a form of an integral. And if one has a varying mass, whether due to the Higgs mechanism you make them big and heavy during the contracting phase, or you make them massless during a conformal symmetry restoration, or due to conformal symmetry restoration, it turns out that those integrals don't converge. As we say, they are not finite, so you evade the conclusions of the old singularity theorems or incompleteness theorems. So it's fairly well cited in the literature, these papers, especially the Bohr's Steinhardt-Turok papers. So I would say that this is very elegant. So that's what shows that you can have cyclic universes that are geodesically complete. Now, I must say that I don't know if you couldn't apply this to just an eternally expanding universe. One should look at it. I think it's an open question, but it's a really important insight, and I would want to emphasize it that the assumptions of the theorems are really important, and loopholes are, of course, always in which of the assumptions are related to which of the assumptions might be relaxed, might be meaningfully relaxed for the physical world, and this is here the constant mass of the particles. But I should say, really, I'm really, really sad that this wasn't my idea. This is something that I would have loved to figure.
Yeah, including the one of the ones that I associate with you. Maybe it's just I can just give you so much praise, but this issue that really appeals to me so much is something that you pointed out to me a long time ago, or a couple of years now, which before COVID, everything seems like decades ago, and that was this idea that the key kind of core idea is that the contraction is slow, and we have this in your model, and we have this notion, the big crunch is like the inverse of the Big Bang, and therefore it's going to be this violent, disruptive, incredibly, monumental occurrence. But if you convince me, that this is not the case. So maybe you can speak about these ideas that you've worked so assiduously on. What is the idea of slow contraction? How does that play in and really solve all these problems that plague previous attempts going back 100 years almost?
I think it's important to look at both aspects of the cyclic evolution. Well, there are really three, but the third one we all know and don't question. That's the current expanding phase, right? So cyclic cosmologists have to tackle three parts. The one is, maybe I'll talk about it in a second, the slow contraction phase. That's the phase that precedes the bounce. And in models of cyclic cosmology, it's really important. This is the phase during which the conditions are being generated that should explain the large-scale structure that we observe today, that you guys observe when you look into your telescopes. The contracting phase is connected to the hot expanding phase by a cosmological bounce. And typically, cosmology and cosmologists, since the introduction of inflation, work in a modular way. So cosmologists are very modular, so you often focus on one phase, try to tackle the problems, and then you hope that you can attach them to the next phase, and then you hope that you can attach them to the next phase. And in this sense, what I believe we all agree on, really, because you and your colleagues have shown it so beautifully and convincingly, is the hot expanding phase. So between nucleosynthesis and today, when we are just entering dark energy domination, there is very little room to wiggle. One can work on what the dark matter is, but that, the large scale evolution is very well described by, if we just, as you measure it, we know that about what percentage of the total energy density is matter, that's enough for us. And it's a very important question what the dark matter is, but that it's not so important from the perspective of, can I describe the large scale evolution? And now when we come to the contracting phase, so let's think in a modular way, so put the bounds aside a little bit, and let's talk about the contracting phase, because that's really something that is something that we can well describe, simulate, and make predictions about, or using it by way of it. And the contracting phases, for just to understand what's happening, it's really important that we often speak about contraction, expansion, accelerated expansion, decelerated expansion, slow contraction, fast contraction. What's really important, to invoke is that within relativity, you always have to think of two scales. You cannot just talk about, what do objects in space-time, for example, two black holes do relative to one another. That's, if they move apart from one another, that's expansion. If the distance between them is shrinking, that's what we call contraction. But for cosmologists, it's very important to look at a second quantity. And this is the quantity that tells us as to how far we can see at a given time. This is our Hubble radius, right? So we have, or we can say it roughly, this is the distance of causal interactions. And now for cosmology, it's really important. And this is something we learned from people who first developed inflation, how important it is to solve cosmological problems, to look at both scales at the same time and the relative dynamics of the two scales. And it's important, as the beauty of Einstein relativity, that the distance between objects, or physical distances, move at a different rate, evolve at a different rate than the Hubble radius, so the scale of interactions, of causal interactions. And what the rate is, it is determined by the matter content of the universe. So what is slow contraction? But let's start with what is decelerated expansion. If the universe is dominated by radiation or matter, then what we know is then the Hubble radius is expanding faster than the distances between objects. And that's the reason why we see more than what was in our causal past. And that's one way of saying that we have an initial conditions problem. Today we know we see actually 10 to the 28, 10 to the 29 Hubble patches that were Hubble patches in the early universe. That is one way of saying we have a problem, because they should not have interacted with one another. Now, slow contraction is decelerating because physical distances expand slower, and it will be important for slow contraction relative to the Hubble radius. Now, if you want to solve this problem, what we learned since the 80s, what you have to do is that physical distances, again, move at a different rate, but in a certain sense, in an inverse way. What do we need? We need that when we start, and that was the original idea of inflation too, when we start with one Hubble patch that has almost the right features, we want to extend the features of that Hubble patch over many, many Hubble patches by the end of this phase. And what does slow contraction do? You start with a huge Hubble patch at very low energies. And what you say is, we will hardly move physical distances towards one another. That's why it's slow. But what moves fast is, on the other hand, you shrink on your physical patch, the Hubble radius at a very fast rate. So slow contraction is slow if you're a black hole or a local observer, but it's very fast from the perspective of the Hubble patch. So all of a sudden you lose sight, very quickly you lose sight of many things. Why is this good? Well, it is good because while this dynamics is occurring, two very important things happen, which we know, and you know, since you are a cosmologist, they are both important. The first thing is obviously we extend local features on super Hubble scales. That's really important because we see today that the same feature extend over exponentially many Hubble scales. So that's given to you. And that's a really elegant, it comes out automatically of the theory. This is, slow contraction means you cannot help it. features become extended over super Hubble scales. But it's a second more important thing, and this is something I've worked on a lot lately. It turns out you can write it down pencil and paper. It's much nicer to do it with a computer. So you can start with any kind of initial conditions. And what I mean is metric configuration. You can very messy geometry. You can have lots of curvature, lots of anisotropies, so shear, directionality in your geometry. Your matter content can be very messy. The only important thing is you have a particular scalar field in there. If you have a particular scalar field, and it doesn't have to dominate the energy density. It doesn't have to have an elegant distribution. The only thing what you need for it is that it has a potential energy which is negative, sufficiently negative, and the potential energy curve is sufficiently steep. Then you can start with almost arbitrary initial conditions. And this will give you a flat and smooth universe. So this is beautiful. And why it's happening? Well, it's happening for two reasons. The one reason is it looks so space-time, and this is something I want to get back to a point that people thought. You remember I said the concern with the contracting universe was not that it's collapsing within Einstein gravity, but it's becoming anisotropy dominated. So everywhere is sheer, and that's not. It's not how the microwave background looks. It's not how a large-scale universe looks. But what happens really is if you have the difference between those considerations and our consideration is the scalar. Once you drop into the scalar field, that could be the Higgs. It could be that the Higgs has a true negative minimum or some other scalar. And once you have the scalar, it turns out that space-time becomes still local. The gradients vanish. So for free, as in every contracting space-time, you don't have to be worried about inhomogeneities. Half of the price is done. Half of the task is done. And the second thing what happens is instead of going to a mess, this scalar with a negative potential energy density tells space-time. I'm talking here metaphorically, but it's really the case what you see. It makes all the difference, since instead of going to this chaotic mess, which is shear dominated, you go to a flat Friedman-Robertson-Walker. So that's the beauty of it. And this is now, so both that the smoothness and flatness is on super Hubble scales, and that it's generated starting from really nearly arbitrary initial conditions. This is something that makes it very exciting to look at these cosmologists. Also because you didn't introduce any different theory of gravity. So everything what you need to explain flatness and smoothness is given to you with Einstein gravity, contracting universe, if there is a scalar field that has a sufficiently steep negative potential.
To next, because you and I had a friendly debate, and again, I'm so grateful to have friends like you that can explain things to me. I'm a simple experimentalist, but I have a great detailed affection for ideas, both classical and new ideas. Like you have brought so many creative new ideas to this field. But I always say that it would be great, if there was an alternative to inflation that didn't have a scalar field, because the thing that most troubles me, until 2012, we didn't know of any scalar fields that existed, let alone one that was cosmologically important. And then, of course, we suspected the Higgs existed, but the Higgs is the only known scalar field. And so I thought, well, it would be great if instead of the inflaton, you shouldn't multiply hypotheses, as I think Descartes said, or somebody said way back when. You should never have excessive parameters, if you will, in modern parlance. And you corrected me because you said, well, what's so bad about a scalar field? You didn't fight back, the way that, say, Sir Roger does, right? Sir Roger has these error bonds, and again, he's a friend of mine, and I push back on him too, because I say, he doesn't have a scalar field per se, but then he has to account for how dark matter evolves, because the dark matter is providing some, version of this effect that you are solving with the scalar field. So now you corrected me, and I wonder if you can recapitulate that. Why is it not so troublesome to have a scalar field in the bouncing alternative models to inflation?
Well, I think, in general, what I wrote to you is it's in general not troublesome to have a scalar field, in my point of view. It's probably one has to pan back a little bit, because a lot of things, how you judge a theory depends on what you expect from a theory, what you think a theory should deliver, and under what condition, what you accept as a good ingredient or as an acceptable ingredient, and what you don't. And I believe, the simple explanation is we haven't found anything simpler that delivers us the same. So I think that, the idea of simplicity with respect to theories is a little bit of a, it can be used in very different ways, but it's always a relative a concept, right? You have two theories, and if they give you the same amount, if they deliver the same amount, then you can say the simpler theory should be preferred. And what do I mean here? Well, first of all, we need the background flatness and smoothness, but we also need the origin of structure. So we also need the source of what reveals its structure, which reveals itself as temperature and isotropies of the microwave background. So if we need that, then we know that those are sourced by some scalar degree of freedom. Now, it might be a condensate. That would not be a scalar field. But right now, our best descriptions are using a scalar. And the second reason why I find, the scalars, and that, you know it because we have corresponded about that we know how to introduce quantum fluctuations for a scalar field on a locally flat background. We know quantum field theory on flat background. And our best knowledge tells us, and our best observations of the microwave background, that the origin of the temperature and isotropies are quantum fluctuations in the curvature, which is a scalar degree of freedom, but we believe that was excited by some scalar matter density, which is a scalar field. So this is a complicated explanation, but the point is scalar fluctuations in a scalar field will lead to scalar fluctuations in the curvature, which will lead to temperature fluctuation in the microwave background. So you need some sort of scalar. That was my answer. And because we excite the scalar degree of freedom of the metric, therefore it doesn't seem to be so unnatural to have a scalar field that does it. Now you could say, well, this is circular, right? You know what you have to do, therefore you introduce a scalar field. How do you know a condensate couldn't do it? How do you know something else couldn't do it? Well, I don't. And, I think that it's important that people look into alternatives. I can live with it because it's overall in theoretical physics. But just because I can live with it, and I think, for me, it's more important right now to figure out if I can, generate a good bounce model, can put it on the computer, and therefore I won't look into it if I can have a better idea. I think it's very important to explore. So therefore, just because I can live with it, it doesn't mean that this is the simplest explanation possible. I think it's simple enough for the purposes that we need it for. But if we had a simpler explanation, then we need another ingredient, because I appreciate that you experimentalists would like to measure directly whatever generates the microwave background. And this invisible field, whether it's during inflation or during slow contraction, is a little bit bothersome, right? So I appreciated that, this is something that, you would like to exchange or trade for something that can be directly measured. So I think people should go for it and see if one can replace it by something simpler. But right now, for the reasons, it's a little bit of a theoretical reasons, I'm not bothered by it. And because it's, overall in theoretical physics.
Let me ask if in the final remaining minutes before I jump on, not a telescope, Anna. Unfortunately, I spend most of my time on telecons, but and I do conversations like these because it makes me sane, and I appreciate it. I want to get, because I can't resist. What is your take on the Hubble tension? Is there something fundamental at work here? Is it more prosaic that we missed the systematic, or and so forth? I'm going to be talking with Adam Rees this week. By the time my interview with you airs, this interview it'll be long in the past. So do tune in the past. I don't know, that violates causality. But anyway, Anna. So he's going to be talking. Obviously, he has new measurement, kind of the percent level measurement of the Hubble constant. Do you think there's anything else that could be going on? Or let me ask you: do you have an explanation, that you prefer hypothetically for resolving this? Is it a fundamental issue that could be shaking things up, or is it more likely to be a systematic error, as I think it might?
You say, I was telling I think it's important if you're a theorist to have good friends. among experimentalists, and you know whom you trust and maybe did a pre-selection or not, or whom you trust more. Of course, you trust everyone, but whom you trust more. And I would say those people that I trust most tell me that it's likely not physics. It's likely systematics. I'm not an analyst, and I'm not an observer. So I would say the people whom I trust would not yet be ready to declare it. That is a mild expression. Some are very sure it's systematic. So I think it relates a little bit how I view this, how I view everything, whether it was bicep 2, whether it's distension or the anisotropy spot. I like to wait it out. I don't like ambulance chasing. So I'm not the type of physicist that writes down a model for every anomaly that one can have. I think it's important. Actually, probably it sounds a little dismissive, but I don't mean it that way. I think it's really important to have people in the field who are very creative, quick creative, and whenever something comes up, they tell you, well, that's what you would need to do in order to accommodate that. But then the second step is also important. If it's complicated, and I would call early dark energy complicated, then probably the lesson is maybe that hints us, either you have to work harder to have a better explanation, or it's really systematics. But I like to, I actually am more of theorist. I like to wait. I like to let experimentalists and analysts work it out first. And then when it's really profoundly established, at the 5+ sigma level, that's when I would turn to it. So I like to follow these debates, but it's more, it's really my approach to these things. I don't think that everybody should have the same approach, but, I have my own approach. I'm more, working on fundamental concepts and trying to make predictions given the theoretical work, and don't tend to jump, at 3 sigma-ish results. I like to wait it out, and I think it's very interesting to watch you guys work this out. And I think it's very interesting to see that the CMB measurements, all of them, whether it's Planck or WMAP, and the upcoming, they agree. So that's probably, I don't know where it comes from, whether it's a late universe, whether, I do follow the talks. I do follow, the discussion between Adam Rees and Wendy Friedman and others and the CMB community, but I would not be willing to write down a theory or even just say what it is. But I must also say that I believe that the early dark energy is not the most attractive explanation that I could imagine, if it's really physics.
Well, in a part 2 in the future, we'll have to get into that, as well as some similarities, perhaps, that you pointed out to me and to others, and the potential for the Higgs field to play multiple roles in the bouncing or cyclic models. But I want to, just touch on what you just said, because I think that's really important. We're talking about educating people, and earlier we talked about, do we teach about the spatial curvature could be -1. It's like, no, we shouldn't do that. I mean, it's like teaching, that there's no evolution or something. But what bothers me, I guess, is that I almost see a parallel. Like, people don't want to teach about, we don't want to teach bouncing models or alternatives in our standard cosmology classes. And it's kind of like, cosmologists working in the field feel like they're teaching intelligent design, or like it just feels so uncomfortable teaching about. I think it's stupid. I think we should. It's a brilliant idea. It's an interesting idea. People have worked on this for decades, and people have an opinion about it that's ill-formed, maybe from decades earlier. But thanks to you, and the reason I bring this up with respect to you and your unwillingness to ambulance chase, which I think is a great metaphor, is a testament to your taste. And I think that you, in particular, in this new generation of young theorists, if I can call you young without being patronizing, are super creative, and that you're not just riding bandwagons, chasing trends. I feel like you are incredibly courageous, you personally, Anna, and I hope that this has inspired some young people in my audience to look deeper into what you've written. And I'll have links to all your vast biography and these phenomenal papers and talks that you give. It's just like, whenever I get to hear one of your talks, and I was adamant a couple of years back when I organized the seminar series at Caltech that you be one of the speakers, because your way of communication is very forceful. It's very logical. It's methodical, and I think it's open-minded. And I think that's lacking so much in our modern cosmology parlance. And I wonder if part of it is because you don't go on social media. It's frustrating because I can't like tag you in all these cool places when you do cool stuff. But anyway, you don't have to respond to any of that, Anna.
I do actually. I'm happy to. I am happy to. No, that's not a problem.
Go ahead.
Look,
yeah.
This is something. I actually think a lot about it. I think what's really important. That's why it's probably a short answer. I have been very lucky with my upbringing, with my family and my schools. I don't think that one should be too afraid of what one teaches kids and what one teaches young adults. One should teach them to make up their own minds. And, if you embrace them, it's very often will be that they won't agree with you. But it's really important that you confront them, especially with ideas that you might not believe in, so that they can make up their own mind. And I am not on social media because I believe look, I appreciate what you are doing and many are doing. And I know that social media has nice aspects. But the problem is it is also encouraging more and more, in my view. And I don't think that, you are prone to that, more, an intellectual conformity, on something that, people are afraid of having a different opinion. That's what's being established as a majority opinion. And, this is not what I'm saying. This is unfortunately something that I experience, and that, right now, this is a problem in our country and a problem worldwide that we have to address, how to make it a positive experience without, eliminating viewpoint diversity. Because we know if we eliminate that and trade it for fear and for conformity out of fear, then we actually stop innovation. And my approach right now is not to participate in social media. I am happy to go on podcasts. I'm happy to give talks. That's my job. But I cannot take, I think right now, the likes and the dislikes and the comments and the retweets. So this is a very conscious.
I always joke. If Galileo had been around and Twitter had been around, rather, when Galileo was around back then, or Einstein, they would have had these blunders and people would have teased them. Or my favorite is Maxwell. James Clerk's Maxwell had the Maxwell equations and Maxwell Boltzmann. He had these wonderful ideas. They're all true. They're all correct. But if you ask what was the microphysics behind Maxwell's equations, there were vortices and gears and whirlpools and luminiferous ether. And he would have been roasted. And maybe, cosmologists would have then had to wait decades, to think about the implications for relativity and the Yang-Mills equations and all sorts of things. So good for Maxwell. Lucky for him that Twitter didn't exist back then. But Anna, now I want to turn to the final thrilling 3 questions that I ask all my honored guests who come on the show. So I wish to ask you final 3 questions in the remaining couple of minutes that we have. Are you willing to go into the impossible with me now, Anna?
Let's go.
Okay, great. So the first one of the thrilling 3 questions has to do with what you put in your ethical will when you reach the age of 120, not material will. But what sorts of wisdom, you touched on some of this a minute ago, but what kind of wisdom would you most want to communicate? Not knowledge, of which you have replete storehouse of, but what wisdom would you want to bequeath in your will?
I believe, I did mention it because this is something, I find important. I think 2 aspects, perhaps. I think it's really important that one should always have the courage to make up one's own mind. And then, more importantly, one has the courage to stand up to one's convictions. I think it's really important, especially when it gets one into trouble. Not to bend. I really think it's important, It's really something that I keep as my life philosophy. Make up your own mind about what's right and do what's right.
Very nice. Very good to hear that. The next question involves going even farther into the future, involves these unseen monoliths that are present in this movie, 2001, A Space Odyssey, came out long before you were born. But it's really kind of a version of Richard Feynman's cataclysm question. When some cataclysm erases all human knowledge, what would you put in a time capsule that really encapsulates what humans are capable of? Kind of brag on behalf of humanity. What would you put in a billion-year lasting time capsule?
That will be boring, but it leads us back to your very first question, why I'm in cosmology. I really would put in, but that should please you, the temperature and isotropy map of the CMB with the equations that describe it. It's really because in order to, first of all, we share this with everyone in the universe, right? This is just our universe. And in that map, it's all of our physics that we figured, and also what we haven't figured. Einstein relativity, the black body radiation, that photons, that light is particle and wave, that electrons, the atomic theory, quantum field theory to understand the 2 and 3 point functions, all the statistics, and what we don't know, where is this coming from? What generated it? Was there a beginning? Where are we going? Dark matter as the, what matter made up what we need, so I really would, this is just, it is a little
funny,
bit,
Anna,
it's talking to the bag, but it's,
yeah. No, I in fact, that was my answer to that same question.
Oh, really? I don't know.
Except I put in the power spectrum because, you can get the power spectrum out is a little bit easier to understand. But like you said, it's visible throughout the whole universe. So actually your answer contains slightly more information than mine. But I think Feynman would be proud of you for answering that way. I hope he would, because your answer obliterates his. His was just that the universe has atoms in it. You've got now atoms, radiation, photons, quantum.
I got everything. But Feynman didn't have access
everything
to the maps, right? Who knows what he would have said. He's one of my great heroes, so I would hope that if I had ever met him.
Absolutely. Last question goes back in time, and it's sort of advice to your former self. And it's the famous statement from Arthur C. Clarke: the only way of discovering the limits of the possible is to venture a little way past them into the impossible. So it's the origin of this podcast name. So I want to ask you, and if you could go back to your 20-year-old self, what would you tell her? What would you give her to give her advice for the courage to go into the impossible as you have already done?
Oh, wow. I'm not yet that old, right? So this is only a little bit more than 10 years back, but I guess, I would probably say that, it's always worth taking the difficult path if that's what my convictions lead me, and that one manages more than one believes one does. So whatever comes at one, actually, when one does the thing that one believes is the right thing to do, one actually gets through a lot more than one would have thought one can do. And I'm not yet old enough to say if it was worth it or not, but I know that I think I would tell my 20-year-old self that I'm actually stronger than I would believe I am if I follow what I believe is the right thing to do. But yet, with the footnote, I'm not yet that old. So it's not really a wisdom. It's more like looking back 15 years in time. I would say that's what I would tell my 20-year-old self.
Well, Anna Ijjas, Dr. Anna Ijjas, it's been a pleasure to talk to you. I hope we can get together in person for one of our long, lingering conversations with you. I always leave it inspired and educated. And I want to thank you for being a teacher to many around the world, and an inspiration of what courage and what integrity looks like as a scientist. Anna, thank you so much for sharing.
Thanks, I appreciate it. Thank you.
Any sufficiently advanced technology is indistinguishable from magic.